Yeah, thanks, Chris. Good morning, everyone. My name is Justin Sorensen. I am a technical sales rep here at Dosatron. And as Chris mentioned, I work in the hydro market, but I have been in irrigation in some way, shape, or form for the last 18 years, believe it or not. And so flow is a term I know well and something that I deal with on a daily basis. Really looking forward to sharing some of that knowledge with everyone and getting you a good introduction to why we use flow, how it's important in dosatron terms, but as well as in irrigation and water management. So, without further ado, let's get going here. So, to start, it is a good idea that we understand some of the key irrigation terms that you will hear in this presentation, but out in the field and in your own experiences. So, we'll start with key irrigation terms as they relate to volume. So the first one we have here is application rate, which is a measurement of the volume of water applied to the crop in a given time. So how much volume have we put down in an irrigation event, right? In layman's terms, an example would be if I have half a gallon per hour in 60 minutes, that means half a gallon has been applied. And we can use that formula to figure out our application rate, how much has been put down for gallons per hour, gallons per minute. But that is going to be what we're going to measure there. Through that, we find drip irrigation is our next term. And drip irrigation is a low volume watering method that delivers water directly to the plant's roots for maximum efficiency. That ties into our next term, our next two terms, which is how do we apply that? So we can do that through an emitter, a drip emitter, drip line. And that is just a small watering device that delivers water at a very low rate and pressure, typically measured in gallons per hour. And it has a certain orifice that then dictates how much of that water is put out. A nozzle and a sprinkler, pretty familiar with those. I'm sure a lot of you folks are, but that is a orifice through which water passes. And that nozzle shape, the size, the placement have a direct effect on the distance, watering pattern, and distribution efficiency, as well as determining how much is let out. So measuring flow is typically done in gallons per day, gallons per hour, which is what we see most, gallons per minute, which is what we use the most here at Dosatron. And then we also use PSI to determine how much pressure is needed for those different nozzles or emitters. Our irrigation requirement is our demand. So the quantity of water needed by the crop. This irrigation requirement is usually expressed in gallons per minute, and it equals the net irrigation demand, gallons per hour, divided by 60 minutes. To boil that down, an irrigation requirement is going to be how much water do I need to apply to my plants to get the best effect from them. Our next set of irrigation terms are going to be related to an irrigation system. Think of your sprinkler system. So an irrigation system is a set of components which include a water source. This could be a domestic tap. This could be a well pump. This could be a freshwater holding tank, but it is our source of water. Our water distribution network, a set of pipes that run from that source to our destination, and then our ways of controlling those. So control components include solenoid valves, controllers, and then we have emission devices, right, our emitters and our sprinklers. Sometimes you might have some other pieces. We have quick couplers, right, where we can tap into our water line at any given time and maybe run a hose, or like a backflow preventer, a device that prevents any dirty water from traveling back into our freshwater source. We have lateral lines or lateral pipes. These pipes are installed downstream from a control valve where your drippers are located. So I think about lateral lines as kind of the, you know, fingers off of the hand, right? So you've got your main component, and then you've got a bunch of lateral lines that are then distributing through your grow and allowing you to place our emitters or our nozzles and distributing that water then to the plants. A main line is going to be where our lateral lines are then traveling from. And so main lines are under constant pressure, and that is coming from our source and headed out to our control valves. A main line will typically have a master valve on it, and the master valve is used to prevent any kind of flooding or overfilling of a tank. And it usually turns on in conjunction with a zone valve. So a zone valve is a valve that's placed at a grow area, and that zone is going to turn on through the use of a controller and water for a specific amount of time, and then it's going to turn back off. When we turn on a master plus a zone, we're then allowing our source to reach our destination. A zone is a section of irrigation system served by one of these solenoid valves. And so zones are comprised of sprinklers or emitters that are of the same rate, meaning that if you have a certain plant on a zone, because we want to keep them similar, we're going to use a similar emitter or a similar nozzle to then water that zone. These zones will typically also include similar water requirements, irrigation duration, irrigation events, and similar substrates or soil types. That solenoid is actually an electromagnetic device which is connected back to a controller, and it opens and closes with the send of a signal. Typically, that's a 24-volt signal, but it can be also 9-volt, and there are some other options as well, depending on the solenoid that you have. But the main thing to, take from that is you send a signal, you can open up a solenoid, which opens up a diaphragm or a ball valve, allows for that water to be distributed. And then when you send that next signal, it then turns that valve back off until it is ready for another event.
All right, so one thing I wanted to jump in and just say, I've got a couple new people that joined, and I just want to give a couple pieces of guidance here. Our goal here is to get to the basics, right? So we're starting with a lot of terminology. This is very text heavy. I think a lot of you will assume, or we have all assumed that, when you see a PowerPoint, goal is just to be very visual. But today our goal is strictly education, right? So again, this can be a resource guide used downstream. So any of you that would like to see this, pass it on to your teams. I see some of our distribution partners here. Just let us know, because the goal is that this is a guide that Justin's walking through that gives those baselines, so that further downstream, we're able to then really start to incorporate irrigation design management, right? So just thought I'd throw that in there. Anyone can raise their hand at any point. There's also a Q&A section here, or a chat. So use any of those to make sure you get the questions across. The Q&A I'll manage pretty regularly. We'll go through probably closer to the end, unless it feels pertinent to that particular conversation. So I thought I'd just let everybody know. So Justin, doing a great job. We'll get through this kind of terminology section, and then we'll go into the meat of it. Thank you.
Yeah. We've got one more slide of terms here, and then we'll really dig in on flow and why that matters. So Our last terms that we'll talk about here is as related to pressure. And so pressure is an acronym for pounds per square inch. It is the force that drives the water for you to make those waterings, right? So when we look at pressure as it's related to irrigation, at least, we find operating pressure. You'll notice in some of the products that you probably use, emitters or sprinkler heads, they have this operating pressure. And that pressure is given in a range, maybe, for an emitter, 10 to 30 psi or 10 to 40 psi. For sprinkler heads and some of those larger watering devices, you might find a higher range. It might be as much as, 60 or 70 psi, depending on how much you need to move through there. But that operating pressure is where we need to start to figure out how much water we need to move and at what force in order for those devices to work. So that pressure is, we can consider static pressure here, which equals less pressure loss. So the more even we can keep it, the better results that we see. When we talk about line or water pressure, you might hear it referred to as PSI or bar, which are the same thing. And that is the force per unit area measured. So why is that important? Well, if we have insufficient water pressure, that can result in uneven distribution of water, poor irrigation coverage. And if we have too high of water pressure, we might cause those nozzles or those emitters to mist or fog, which also leads to waste and inefficiencies as well. Pressure loss is what we lose through a system as the water travels from point A to point B, and it's synonymous with friction loss. And so for every elbow, for every turn, for every length of pipe, there is a certain consideration we take when it comes to pressure loss, knowing that we start with pressure at point A and we end with a less pressure at point B because of where we had to travel and that friction loss. So always take into account your pressure loss in order then to determine, do you have ample pressure at the end to make those waterings based on your operating pressure. We can use pressure regulators to help distribute that more evenly. So you may find that your starting pressure is quite high, and that's in order to move the water a distance to your point B or your destination. At that then destination, before we send that out to our emitters or our nozzles, we can use a pressure regulator. We can bring that pressure back down and evenly distribute it through our lateral lines in order to feed out to the plants and give that consistency and that even distribution. And then working pressure, the pressure of the irrigation system during operation. So as a pump turns on or as the water starts to move through your zone valve, what is that holding PSI that we see? That would be what we consider working pressure while the system is operating. Okay. So now that we've gotten through some of the terms, I hope you have a better understanding of just, irrigation and all the parts and pieces that we really take into consideration and all these, different things that are going to ultimately determine how we think about flow. And so what is flow, right? Flow in irrigation is the movement of water from that source to that destination. That's a very reoccurring term that we hear a lot of is, how are we moving our water and where is it going and where is it starting? And so that is used typically for watering of your crops and your plants. Flow is then determined by the amount of water dispersed over a given amount of time. And this can be influenced by changes in pressure. So think regulators or think pumps, restrictions, which nozzles and emitters help us do. And then the last piece is time. and that's irrigation events or irrigation durations. So flow is typically given in gallons per hour, gallons per minute, or gallons per day. Can also be given in liters per hour, liters per minute, or liters per day. So an easy example to think of when you're determining flow is if we have a flow rate on a zone of 10 gallons per minute and we have an irrigation event of 30 minutes, we have 300 gallons of total flow occurred. We can also then, for everybody out there that maybe wants to convert from liters to gallons, I've included here that transition. And so the conversion is 3.79 liters per gallon. So 10 gallons equals 10 times 3.79, which gives us 37.9 liters. If we want to go from liters to gallons, we just simply divide the number of liters by 3.79, and we've reversed that formula. So why does flow matter? In irrigation, we use flow mostly to determine consumption. So besides figuring out how much water you're putting down, um, you know, we really want to look at how much water is being consumed. And so consumption can be either from a freshwater source, a batch tank solution, or we can use flow to determine the amount of nutrients we would use in a given irrigation event. Very, very fine detail, right? So from freshwater source or batch tank, it's quite simple. It's just the rate of flow multiplied times the length of an irrigation event. So a flow rate of 5 gallons per minute and an irrigation event of 5 minutes gives us 25 gallons consumed. Now, that can be 25 gallons from your freshwater source, or it could be 25 gallons from, say, a batch tank that you have already mixed. Now you can kind of figure out how long will this batch tank last me if I have 5 gallons per minute of flow. So you can start to determine how often am I going to have to fill it? What do I need to fill it to for, say, a daily watering? Gives you some of those details and leads you to the place where you can really become efficient and really save solution, save water, save nutrient. But all of that really plays into figuring out first, what is my flow? So when we look at from a stock tank, or how much nutrients are we going to use based off of our flow, we take the rate of the flow, we multiply that times the length of an irrigation event, and then we take that total and we multiply it times the rate of injection, or what our injector is set to. So flow rate is 10 gallons per minute in this example. And we have an irrigation event of 10 minutes. And my injector is set to 1%, or 37.5 mil per gallon. So first, I want to figure out what is my flow rate times my irrigation event to get my total amount of water consumed. And so that comes out to 100 gallons. Then we take that 100 gallons and we multiply it times what our injector is set to. And if it's 37.5 mils, we come out to 3,750 mils of stock concentrate was used in that 10 minutes, or in that 100 gallons. So for reference, 1 gallon is equal to 3,785 milliliters. So we're just at about a gallon of concentrate used per watering event of 10 minutes at 10 gallons per minute of flow. Why is this important? Well, I know that if I'm going to mix a stock tank and it's 50 gallons, I would run out after 5,000 gallons of irrigation are ran. We can also use ratio here. And so at a 1 to 100 ratio, for every 100 gallons ran, I'm going to use 1 gallon then of my stock concentrate. And so at 5,000 gallons divided by my 100 will give me 50 gallons of stock used. Why flow matters when we're talking about shot size. So this may be an application that is less used in our industries, but determining how much is applied to each plant site for a given watering time can become a super important tool when it comes to managing water content of your substrate or your soil, but also in efficient watering as far as saving on consumption. So if you're able to really boil it down and get very, very granular and microscopic here, we can figure out how much each plant is getting based off of knowing what our flow rate is. So let's look at this example here. I have a zone, and each one of my plants on that zone is getting 1 gallon per hour. That could be a single gallon per hour emitter or two half-gallon per hour emitters, right? But the total flow rate at each plant is 1 gallon. So from our previous example, we know that 1 gallon is equal to that 3,785 milliliters. Now we can use the flow rate multiplied times the length of the irrigation event to determine what is our shot size. So flow rate equal to 1 gallon per hour or 3,785 mils per hour. We divide by 60 minutes and we get roughly 63 mil per minute. If I ran that zone for a minute, I'd be applying 63 mils to a plant site. Say I want to give it a shot. I want to do some more pulse irrigation. I want to do some more steering. I don't need to give it a full 63 because, I'm already at a certain percent of water content in my substrate. I only want to do a 15-second shot, but how much is that really going to be for me? Well, we can figure that as 63 divided by, 15 seconds there. And we get about 15 mil applied to each plant site. This is going to really help a lot of people when you start to boil this down to figuring out how much am I putting down per minute? Well, actually, how much am I putting down per second? I can really start to get finite in my numbers and get that consumption of how much am I really using here and how much am I wasting, right? Because the biggest thing we can do is avoid this waste and water more efficiently and keep our substrate at a water content that is really beneficial for us. The plant is eating and making the most of the nutrients. And at the end, you get the best overall product with the least amount of input is really the best way to look at that. How do we calculate flow rates? If we have existing irrigation, the formula, it really becomes quite simple. And so we're going to take the number of emitters or outlets on a zone. So it could be nozzles of sprinklers. It could be, drip tape with 12-inch spacing, or emitters that we have plugged into our drip line ourselves. But the number of those outlets times what the rate of each outlet is in gallons per hour. If it's not in gallons per hour, that's okay. We're still going to figure it out and get a total gallon per hour or total outlet of that zone. We then take that total GPH and we can divide by 60 minutes. By doing this, we now have figured out what our total gallon per minute of the zone is. And effectively, now we know what the flow rate is for that zone. In this process, we've also figured out what each plant is getting by knowing the emitter size in gallons per hour. So if you have 300 emitters, each with a flow rate of half a gallon per hour, and you want to find your total flow rate for the zone, you're going to take 300 times 0.5 gallons per hour, and you're going to get 150 gallons per hour of flow rate on that zone. That 150 gallon per hour is then divided by 60 minutes in order for us to get the gallon per minute of the zone, which here is 2.5 gallons per minute. So if you do not have irrigation existing, but you're looking into, say, Dosatron, and you know that this irrigation system, this injection system has a minimum and a maximum flow rate, you can start to determine what irrigation would work best for you or what your options could be for setting up this irrigation. And so the first thing we want to do is calculate what our minimum flow rate per plant would be. So we take the minimum flow rate of a system multiplied by 60 minutes to give us the total minimum gallon per hour of the zone. We then divide that minimum gallon per hour flow rate of the zone by the number of plants that will be fed on that zone. And that is going to give us our total minimum flow rate for each plant site. In our example, we use the hobby cultivator system here that has a minimum flow rate of half a gallon per minute. We have 100 plants on our zone, and we want to know what's my minimum dripper I can put at each one of these plants. So 0.5 times 60 minutes gives us 30 gallons per hour minimum flow rate. We take 30 gallons per hour, divide by our 100 plants on the zone, and we have found that we can put a 0.3 gallon per hour dripper at each one of our 100 plants and hit the minimum flow rate of the system. Maybe I want to go with a larger emitter, but how large can I go? Well, let's figure out the maximum. So we do the same equation, but this time we're going to use the maximum flow rate of a system times our 60 minutes, and then we get that total GPM of the zone. And we can then divide that by the number of plants, just like we did in the minimum, and get a total max flow rate per plant. So same scenario here. We have 100 plants. We've got a hobby system, or we're looking to get the hobby cultivator system, and it's got 5 gallons per minute max flow rate. So 5 gallons per minute times 60 minutes gives us 300 gallons per hour maximum flow rate. We divide 300 gallons per hour by the 100 plants on our zone, and we've now found that we have 3 gallons per hour per plant maximum. I have now figured out that if I'm going to put in this irrigation system and I want it to operate with this system, I will have to put emitters that are above 0.3 but below 3 gallons per hour for each one of my 100 plants. If I do that, the system will work. When we select dosatrons, we're going to consider first, what is our flow rate? So by determining our flow rate, we can determine then which injector will fit within our, say, minimum and maximum flow rate in a facility, in a greenhouse, in a outdoor crop. But we need to figure that out first so that we know what series that'll fit into. Between all the irrigation units that we offer here at Dosatron, we can work between the flows of 0.5 gallons per minute all the way up to 400 gallons per minute when we have our units in series. And so by in series, I mean that we have a dosatron followed by another dosatron followed by another one, and it may be three, four, five, six. It may only be two, but they are in series with each other. The other way that we can use dosatron, and this is to double our flow rate, is we do a system that we call parallel. So by placing units in parallel, we can double the flow rate for any series of injector. 2 times a D40 in parallel will allow us to then increase our flow rate, maximum flow rate, to 40 gallons per minute, or 80 gallons per minute, sorry. So 40 for each D40 then gives us 80. The important thing to remember here is that when we go in parallel, we want the units that are in parallel themselves to be injecting the same input, so the same fertilizer, the same chemistry, and we want those to be set to the same injection rate. And why that's important is that if we're not fully at 80 gallons per minute, there's a chance that some of that flow, a higher portion of that flow, could be traveling through one of the injectors versus the other. If they're set to the same rate and they're injecting the same thing, we're still going to achieve the proportionality of injecting a set amount per gallon of water for every gallon that travels through. So let's talk about some of the different dosatrons that we have in the irrigation field here. The first is going to be our lowest flow range, and it is the hobby cultivator series. So our flow range on the hobby cultivator series is 0.5 to 5 gallons per minute. It has an operating PSI of 35 to 87, and it is a 3/4 inch inlet and outlet. In this series, we have one injection range, which is 1.875 to 18.75 mils per gallon, or 0.05 to 0.5%. This could be purchased as a 4-unit, 5-union system, or as single injectors, 1 unit, 1 union. From there, we move up to our low flow series. Here, we can find that a single injector in line is going to be 0.05 to 14 gallons per minute injection range. However, when we start to place them in series, that flow rate minimum and maximum now goes to 2 gallons per minute to 10 gallons per minute. Our operating PSI is 4.3 to 85, and we have a 3/4 inlet and outlet. Now, in this series, we do have multiple dosing ranges. And so we can see that from our D14 MZ3000, we can achieve 1.25 to 11 mil per gallon, or 0.03 to 0.3%. We can move up to a 1000 to achieve a 3.75 to 37.5 mil per gallon injection, or 0.1 to 1%. From there, we move to a D14 MZ2, which is 7.5 to 75 mil per gallon, or 0.2 to 2%. And then finally, we have a D14 MZ10, which is 37.5 to 375 mils per gallon, or 1 to 10%. So through the 4 different models of dosers in the D14 series, we can do anywhere from 1.25 to 375 mil per gallon. These can also be ordered with different seal types. So the first seal type we have is Viton, which is a pH of 7 or less, more acidic products. If we have a more caustic product, a pH of 7 or more, we would want to order it as an A-flas seal. The third seal type is if we are doing continuous use of oxidizers or highly concentrated acids. If that's the case, we want to spec it as a CalRes unit in order for those seal types to be compatible with those highly concentrated acids and those oxidizers.
Yeah, and I'll jump in, Justin. When it comes to seal types, this is one of those considerations, that across the board we have. You'll notice that our standard is always Viton in both the hydroponics, horticulture, greenhouse, kind of any irrigation sector. Viton becomes your standard. So those of you that don't really worry too much about seal types when you're ordering, you're more than likely getting the right thing, right? Because so much of what we do in this world is acidic or neutral to acidic. Now, when it comes to the world of hydro, we've seen a big increase in pH up over the last 5 years, specifically the last decade, but let's say even the last 5 years targeted. And that's where you've seen more introduction of the A-flas seal. Now, there's only really particular chemistries that the A-flas seal is what we consider necessary at the beginning of ordering. And that really is just to extend the life of those seals, right? So at the end of the day, the rule of thumb is you get Viton and it is a pH up product. Maybe you find out downstream, or you're going to change products with a Dosatron. There is the ability to change those seals in the field, right? So just keep that in mind. A-flas seals can be ordered for any of these units that Justin will go through, and you can change that in the field. That goes the same with the CalRes. The CalRes seals are quite expensive. So often you'll find us when CalRes is asked for, required, just that we dig into that and make sure that that's the right fit. Again, can be field retrofitted, no problem. There will be an increased cost in that. But when you're using an oxidizer like peracetic acid on a regular continuous basis, you'll find those CalRes seals to be 5 to 10 times more life than what you'll get out of a standard Viton. So just keep that in mind. And when we say concentrated use of acids, often people then think, oh, okay, I'm going to inject an acid, I need a CalRes. No, that's because if you're using an MZ2, which is what our standard unit is, which is 1 to 500 to 1 to 50, you're going to find yourself diluting that acid down to a concentration that is not nearly as affected, or the seals are not nearly as affected by that product. So just keep in mind that not always is CalRes the way to go when you're doing acid, though it is, of course, going to extend the life of the seal in given circumstances. The highly concentrated acids, if we're in an instance where we're filling some sort of freshwater tank with an acidic solution to, combat our bicarbonate load, well, then, yeah, let's go CalRes and let's use that particular product with that. So I thought I'd just add that little bit into where you're headed, Justin.
Yeah, thank you. And if you're ever unsure of the product that you're using, there are some really good websites that have Viton compatibility. They have A-flas compatibility, or you can even look up CalRes compatibility. I would find that CalRes is almost compatible with everything that I've ever searched. Being that it is, a very expensive seal, though, if your Viton is compatible, then go ahead and use that and feel free to. And then if you really just don't know, get with us, give us a product, give us maybe an SDS sheet, and we have resources. If it's not something that we've already dosed before, we have some resources that we can reach out to and look up and make sure that you're getting the correct seal type. So, all we would really require there is a SDS sheet or a product label that gives us an idea of what the composition of that chemistry is or that fertilizer, and we can steer you in the right direction there. The next unit that we're going to talk about here is Midflow D6 series. So you may not be familiar with this unit. This unit is actually quite new for us. And this is a doser with a flow range that has 0.44 to 26 gallons per minute as a single injector, or 2 to 26 gallons per minute in series. If you are a current user of the D45, this unit is going to be a better option than the D45 as it's got a better flow range, and also upgrades to the piston and how the bell housing connects to the body, how the actual piston is operated inside of the unit. Just a lot of different upgrades have gone into this to make this unit, really bulletproof. I mean, it is pretty impressive how this thing is assembled and how everything operates on the inside of there. Tons of upgrades, and so this unit here um, does have a 4.3 to 116 psi operating psi. The connection size is 1.25 inlet and outlet, so can be bushinged down to 1 inch. Could also be bushinged up to 1.5 inches. We should be able to get 26 gallons per minute through 1 inch pipe. Definitely can get that 26 gallons per minute through 1.5 inches. So either way you want to go there, depending on what is existing in your facility or in your operation, it'll fit in very nice there. Uh, does have multiple dosing ranges as well, as our other units that we see. And so the D6MZ3000 gives us that 1.25 to 11 mil per gallon, or 0.03 to 0.3%. We also have a 1000 version of this, which gives us that 3.75 to 37.5 mil per gallon, or 0.1 to 1%. And then we have our D6MZ2, which is 7.5 to 75 mil per gallon, or 0.2 to 2%. This unit, just like our low flow and our high flow and some of our other units, can be ordered with the different seal types depending on what is being injected. Our next series up is the high flow D40 with a flow range of 2.2 to 40 gallons per minute as a single injector, and then 5 to 40 when placed in a series. PSI operation is 4.3 to 116, and our connection size here is 1.5 inches. We need the larger pipe to supply the higher flow rate. Our dosing ranges, very similar to other dosers. We have that D40MZ3000. Here you'll notice though that we're at 1.25 to 7.5, not to the 11 like you see in the mid flow and low flow series. It is 0.03 to 0.2%. We then go up to the D40MZ1000, which is 3.75 to 37.5 mil per gallon, or that 0.1 to 1%. We have a D40MZ2, 7.5 to 75 mil per gallon, or 0.2 to 2%. And then our largest injection range is the D40MZ5, 37.5 to 190 mil per gallon, or 1 to 5%. This one can also be ordered with the 3 different seal types. When we step into above 40 gallons per minute, we're going to start moving into what we consider our mega flow units. And the first one we have here is the D20S. This is a workhorse of a unit. We can do anywhere from 5 at a very, very low flow range for, considering this unit, up to 100 gallons per minute. We can also operate at a low PSI of 2 up to 120. Our connection size is 2-inch inlet and outlet, and we have a single injection range for this D20, and that is 1 to 500 to 1 to 50 or 0.2 to 2%, and it comes with standard Viton seals. If we need to go higher than 100 gallons a minute, our next one in the MegaFlow series is our D132. Our D132 operates in a flow range of 35.2 to 132 gallons per minute. And our PSI is 7 to 87 PSI. Connection size is 3-inch inlet outlet. And then we've got 3 different models. So here we can do a 1 to 30,000 to 1 to 3,000 or 0.003 to 0.03%. With our D132 MZ5000, we can do 1 to 5,000 to 1 to 500 or 0.02 to 0.2%. And then the MZ1, 1 to 1,000 to 1 to 100 or 0.1 to 1% injection. Also can be ordered in the 3 different seal types. Finally, we have our highest flow rate injector in the MegaFlow series here, and that is the D400, which gives us a flow range of 110 to 400 gallons per minute. Operating PSI 7.25 to 116. It has 4-inch flange inlet outlet connections. And then we also have 3 different dosing ranges. So we can go from 1 to 30,000 to 1 to 8,000, 0.003% to 0.0125%. We have a D400 MZO2, 1 to 5,000 to 1 to 500, 0.02 to 2.2%. And then an MZO5, which is 1 to 1,000 to 1 to 200, or 0.1 to 0.5%. And once again, can be ordered with any of the seal types. So now I'd like to open it up. If there's anybody that we have any questions, we can check in on the chat. I'd love to hear if there's anything else I could go over, or if I could provide any information for you. Just go ahead and let us know there in the chat.
Yeah, so let's see. George raised his hand. Hi, George.
Don't know if he's able to.
You might have to go into Q&A. Doesn't look like we're able to hear you, George. If you throw your question in the Q&A, we'll make sure we get it answered. All right. Well, just until we get George's question written, one of the things I thought I'd touch on too was the fact that our D132 and D400 use our trusted units, the D14 and the D40, with that diversion technology. So just keep in mind they're reliable, they're robust, they have a huge, customer reliability stance, and they're doing a great job for us out in the field. So, all right. So Jose's asking, can you explain why the flow range changes when the injectors are in series? So Justin, do you want to take that, or you want me to jump into it?
Yeah, I can take that. So Jose, to answer your question, when we're talking about flow and how that flow is going to move through the dosatrons, as a single injector, we have that piston, and that piston's moving up and down. And so as that flow is moving through there, we are seeing some friction loss, and we're also seeing a little bit of distortion in the, how that flow moves. So when you start putting multiple units in series, We actually want to increase our flow rate in order to achieve that similar injection that we would at the single injection level, right? And so that's where we go from a 0.05 on a D14 to 2 gallons per minute when we start placing multiple injectors in series.
Yeah, and it really just like you couple a friction loss, right? Across the unit, right? So much water has to touch the bodies of the dosatrons. Then the dosatrons themselves are using that water pressure and volume to move, right? So there's what we consider kind of dynamic turnover. You start lining up dosatrons, and you want to make sure you get turnover from product to product and good adequate blending. So really the flow rate low end really has a big influence on that. It also has to do with just straight functionality of the dosatrons. Again, as we steal some of that pressure and flow as we go through each dosatron, that's why we will always recommend a pump with some sort of variable frequency drive or upstage to be able to see that pump kind of help make up the differences in flow and volume to make sure we can have adequate pressure and volume coming out of the end of the dosatron. So it's good. George had a question. Do the units come with and without internal bypass? The answer is yes. So there's a switch that goes on top, and as that piston's moving up and down, again with that water pressure, changing the open and closing of those internal valves, and you hear click clack click clack. What the bypass is doing is literally throwing a rod down into that, stalling that piston with all 4 or 6 or 8 valves, depending on the unit, open to allow full pass through of volume and flow, but not to inject the product. So that will stop the injection, still allow water to pass through. So it's a great question, George. Kyle has a question. When filling batch tanks, is it best to use flow restrictors to make sure you are not outflowing the injector? Even though the dosers are rated for a certain flow, there's a sweet spot. Kyle, great question. Kyle's been a great distributor for us for many years. So Kyle, I'll jump into that one. When you're filling batch tanks, using flow restrictors do help. Now, to your point, especially when we're oversizing a pump, right? So often we're going to oversize a pump, or we're going to have a pump at a main header station, and that header could be 2-inch volume, or I'm sorry, 2-inch in size, therefore increasing volume. And therefore, let's say you're feeding an 1.5-inch Dosatron system, which is only rated for 40 gallons a minute. Yeah, we're going to probably want to put a flow restrictor, which is a volume restriction, therefore manages only 40 gallons a minute comes through the system. Why that really helps is now we can line up multiple Dosatron systems off that main header and not have to calculate about how much is coming through it with, let's say, a ball valve at the head or something else. So it is a restriction that makes sure that 40 gallons does not surpass, and then we can kind of get what we need out of the Dosatrons. Let's say we turn on multiple Dosatrons off that main line, we drop our flow rates down on each one. The restrictor's it's not going to hurt anything at 30 gallons a minute, right? It's just going to make sure nothing but 40 goes through it. So it's a great question, Kyle. And I'd say, yes, there is a sweet spot, both in flow and in injection and pressure, right? So some of that is about balancing all of that when we're in multiple dosatrons in a series.
And I would even go a little bit further too, is if you know what your flow is at the batch tank level, being able to then, if you want to do a time fill, right, hey, I'm at exactly 10 gallons a minute at my batch tank. If I do a 10-minute fill, I'm going to be at 100 gallons. If you don't exactly know where you're at, then those time fills become a little bit more of like a trial error and trying to figure out, man, what is my flow at that batch tank level, right? So twofold, right? You can also then say, I know exactly what I'm putting it in at what rate, and I can then determine by a time fill how much is going to go in there.
Yeah, that's a great point, especially because of a lot of times with Dosatrons, we're not using a sophisticated control system that's going to manage that automatically. So having those down and understanding those fill rates, absolutely, and being able to target that absolutely can make all of that math pan out to more, something that we can rely on, right? So great point, Justin. We've got just a few more minutes before we'll call it at the hour. So, I want to make sure everybody gets a chance to throw in their questions if they have it. Thank you all for being here. Oh, George has one more question. These units need external support when installed in addition to the support the pipes provide? Are they heavy? Oh, that's a great question, George. I will say I've seen everything from what we jokingly say we've seen, duct tape and zip ties to hold up Dosatrons, to, obviously more of a commercial or mechanical plumbing style where we're using strut clamps and we're using unistrut and all of that, everything in between. So the best advice we can give is that Dosatrons themselves do not come with mounting systems for the pipes. So each Dosatron comes with its own bracket that then you can fasten to a wall, to unistrut, to attachment devices that then allow us to mount it just about anywhere. We have Dosatrons mounted kind of in the middle of rooms in some of these water rooms. And a lot of times that's based off of like a unistrut frame, right? Unistrut being that kind of channeled strut that we can attach brackets and hardware to mount the Dosatrons to. So that is what we recommend as much as possible. Using pipe clamps is not always easy because the Dosatron inlet outlet doesn't match up to where the bracket actually attaches. So that's where we will advise two lengths of unistrut, one for the Dosatron brackets, one mounted directly butted up against it for the pipe, right? And then we can add pipe fasteners in that. Now, when you run horizontal pipe or horizontal unistrut, there's only a few pipe clamps that work. So we advise using some pipe clamps that we actually sell here at Dosatron. Our distributors also provide, which are called quick clamps, 2Ks, quick clamps. So any of those questions we can definitely answer downstream. But yeah, we want to try to provide support to the pipes, but the Dosatrons will come with support brackets. A little bit of both would reassure that weight of the water itself doesn't create any issues. So good question, George.
Yeah, a system empty is a lot lighter, and then you fill it up with water, and we're talking, 20 to 30 gallons of water that might be in that full length, depending on how many injectors and stuff you have. You're then just adding that more weight. So besides the Dosatron brackets that are included with each Dosatron, having the additional pipe support is a great idea.
And we do sell a kit that allows you to mount those Dosatrons onto a wall. Comes with some strut and hardware to do so. So
Cool.
Inquire about that in the future. All right. Well, listen, we're at the hour. We're actually 1 minute over on my clock. So thank you all for being here. Thank you, Justin. I know that this was a bit more, again, educational heavy. Hopefully people learned some things. We wanted to make sure to go over very specific definitions. And then this will build up to our next webinar. Our next webinar, we're really going to talk more about the application. We're going to talk more about downstream. What can we do with Dosatrons and how do they fit in? But let's also just give you some more education on how irrigation systems work, how we can define those irrigation systems, what's a good fit for all of us as we build new facilities or expand upon our existing, and how can Dosatron be a great partner, and how can we make sure that we find other avenues that we can supply goods and parts for your irrigation system. So let us know what we can do to continue to improve. We appreciate you all being here, and please keep in touch.
Yeah. If I wanted to leave everybody with something here, appreciate you coming and learning about flow with us today. From what you can learn about flow, you can learn about where am I applying that flow, and anywhere that you are using some type of a emitter or nozzle or even a hose, we can put a Dosatron to allow you to add something to that water for wherever you're applying it. So this was more focused and geared towards figuring out flow and irrigation systems and how all that works. But then you can really think about it and say, well, I've got a hose here and I've got emitters over here and I'm doing this. Can I put a Dosatron here? And the answer is yes. And we can do a wide range of different things and inject a wide range of different chemistries and fertilizers, and then allow that to enter the flow to then be fed out to those crops and plants. So appreciate everybody today. And I hope you learned something, and thanks for attending.
Thanks, Justin. Thanks, folks. Have a wonderful Friday. Enjoy your weekend.